and welcome to the IUPUI Center for Translating Research into Practice August Scholar of the Month conversation with Dr. John Goodpaster. My name is Steve Vieweg. I'm the Associate Director of the Center. My pleasure to welcome you here. The Center for Translating Research into Practice seeks to identify, celebrate, and promote research that is translational or that is interdisciplinary, that generates or uses generated knowledge to solve complex problems in our community. We're grateful for our beginnings, our humble beginnings, from Dr. Sandra Petronio, Emeritus Professor of Communications, who came to campus some years back and recognized how much translational research happens here at IUPUI. Our current director is Emeritus Chancellor Charles R. Vance, who helps lead us in the continued efforts to make sure that this sort of research is available across our campus and in our community. We're delighted to have you here with us today, and we are welcoming Dr. John Goodpaster, who will talk to us pretty soon, but I want to give us some beginnings here and remind us about Zoom etiquette. Everybody's familiar with Zoom, but just as a reminder, please be sure to keep your microphones muted, and you can leave your videos off at the beginning so that we have plenty of opportunity to hear our initial comments from Dr. Goodpaster. We encourage you to type questions and comments into the chat, and there'll be time for conversation at the end of his initial presentation. We are recording the presentation for future reference, and you will receive a post evaluation. We'd love to hear your comments and thoughts as we plan for these amazing monthly conversations with our scholars. The opportunity now is available for you to get credit. If you're interested in getting some continuing education units, all you have to do is search for Expand at IU's website, and you can sign up and get credit as you attend these monthly sessions. We hope that you'll take advantage of that and tell your friends about this opportunity. You can always follow us at the center about what's going on in the area of translational research. You can find us on Twitter, Facebook, well, you pick it. We also have a YouTube channel where you can find video interviews and information about our translational scholars. I'd like to make sure that you know information's available in lots of other ways, including the research articles. So if you go, for example, to our TRIP website, and go to the featured scholars. If you click today on John Goodpaster, our speaker, you'll be able to see some more information about him and see some of his works that are available on something called ScholarWorks, where you're able to see many of his publications free and easy for you to read. Or you can go just directly to the ScholarWorks page and see more information about his work. This is an amazing resource available to anyone in the community so that you can access the work of our scholars and be able to understand and ask questions and get involved with us as we work together to solve complex problems in our community. So coming up next month, we are going to have our conversation of the month with scholar Sylvia Bagatti, and she'll be talking about a community-engaged and strength-based approach to fostering well-being in Latinx communities, and that's scheduled for September 24th. You can always check out the schedule of other events coming up on our website. Today, we are delighted to have with us Dr. John Goodpaster, who's an associate professor in the Department of Chemistry and the director of the Forensic and Investigative Sciences program here at IUPUI. He teaches about alcohol, drugs, and trace evidence and conducts research on ignitable liquids, controlled substances, and explosives. And we're delighted to have him with us here today so that we can learn more about his work and have a conversation with him to see what we might learn and add about this work. So please help me give a warm IUPUI Hoosier welcome to Dr. John Goodpaster.
Well, thank you very much. I'm going to go ahead and share my screen, and we can go through some slides talking about our research. Okay, does that look okay to everybody, hopefully? Okay, excellent. All right, well, we're going to talk about chemical analysis. I'm an analytical chemist, and so analytical chemists are concerned with making very careful and exact measurements of various systems. And we're going to talk about chemical analysis as a tool for both arson and explosives investigations and the kind of efforts that have been going on in my group in that area. So let's start with a really broad definition. What is forensic science? So I'm a forensic scientist, and the broadest definition of that is that the forensic science is an application of science to the processes of law. So I'm a chemist by training, but I'm applying chemistry to things that are legally relevant, like a criminal investigation. And so therefore, I'm practicing forensic chemistry. You can have any other type of science that you can think of. If it's applied to something that's legally relevant, that's the process of law, then that can be a forensic science. So obviously chemistry, biology, physics, a whole assortment, psychology. These are all considered forensic sciences. Now, criminalistics is a little more specific. So criminalistics is also the umbrella term for what I do. And that is distinguished by the analysis of physical evidence. So actual matter or material that you gather from a crime scene, a suspect, or a victim. And that can be all sorts of different things. So I've got a list here of possible fields within the greater field of criminalistics. Trace evidence is really where our work falls. So typically or traditionally, arson and explosives investigations are a form of trace evidence, but that also includes things like hairs, fibers, glass, paint, you name it, can all be analyzed as trace evidence. So here's one of my favorite quotes, and it's about the power of trace evidence. It's attributed to Paul Kirk, who was a very famous criminalist in the 20th century. And I won't read it word for word, but I do want to point out a couple of things. One is that the principles of trace evidence are such that no matter what, whatever environment you are in, you will tend to deposit trace evidence in that environment and pick up trace evidence in that environment. That's called the Lacard exchange principle. And these types of trace materials can be thought of as mute witnesses. So they are simply materials that have no agenda. They do not have flaws of memory. They don't have any kind of bias. And it's really up to scientists, like trace evidence scientists, to look at that evidence and discern its meaning. And so that's where chemical analysis comes in, is that the analysis of physical evidence in the form of trace evidence can tell you about circumstantial links within a criminal investigation. And those links are primarily forged between the suspect, the victim, and the crime scene. So when you think about forensic chemists, their job function falls into one of two different areas. So the first is just identification, which is you're given an unknown and using the tools of chemistry, identify what that material is. So some examples are listed here. For example, given a blood sample, can you identify ethanol or ethyl alcohol present in that sample and at what level? Is it above or below 0.08, for example? This white powder substance that you see in the slide, that could be heroin or methamphetamine or cocaine or methcathinone or any number of different organic compounds that are controlled substances. It's up to a chemist to take it from a white powder to then analyze it and then deduce and confirm its identity. Explosives falls within this. So you have to identify the presence of an explosive in an explosive device, either before or after it is detonated. Ignitable liquids, same thing. You go into a fire scene and you have to try to identify whether or not an ignitable liquid might be there, because that would be a strong indicator of arson. Then the other job function is comparing. So this is usually where you have two samples. One sample has a known origin, like it's known to have come from a suspect or a victim or a crime scene. And then you have a question sample or an unknown. And you then carry out a series of tests, compare the characteristics of the question sample, the Q, then the known sample, the K. And as you get to the end of those tests, you can make a determination as whether those two samples could have had a common origin. So for example, fibers from a victim's shirt may have been found on the suspect during a violent altercation. And so you compare those fibers taken from the suspect, fibers from the victim, look at the characteristics and try to determine if they are the same. Because if they are the same, that means there's some chance they could have come from the same place. All right, so now we're into the research part of this talk. And so I'm going to talk about 3 different sub-projects. The first I'm calling Beating the Bugs, because this project was about preserving fire debris evidence. So in a fire, if an ignitable liquid is used, it is relatively common for residues of that ignitable liquid to remain. So no fire is 100% efficient. And so the residual fuel, like if you're using gasoline to start a fire, the residual fuel or residual gasoline is still there, and you can try to identify it. What happens, however, is if you are looking at a fire like this, in this picture where you've got fire on top of a grassy soil type of matrix, there are certain species of microbes that live in soil that also happen to have the ability to actually consume gasoline and other petroleum products. So they will actively eat the same chemical compounds that are in these fuels and use them to turn into energy and to reproduce and so on. So when I first learned about this, I was surprised. I didn't think that bacteria would want to have anything to do with things like gasoline, but there's certain species. And this photograph actually shows you a microscopic image of the species of bacteria that we were dealing with. It's called Pseudomonas. So it's a pretty large genus of microbes, but it has this ability to metabolize things that are not natural, so things like distilled fuels and so on. So normally in a fire scene, you have a pretty strict list of things to do. You're looking for both the cause of the fire and its origin. So you want to try to identify where the fire started. That's the origin. You then will excavate or go below the surface level and look for residual fuel. This picture shows you these dark stains in the carpet padding underneath this carpeting. And those are from the fuel that was poured there. So somebody poured a liquid that seeped through the carpet and into the carpet padding and burned. But even though it burned and then the fire was extinguished, you still see these residues. So carpet padding, for example, is a very common type of material in fire investigations. So you collect that. You then can collect comparison samples if they're available, and then analyze those and try to identify any kind of ignitable liquid. And in cases where there's lots of residue, you would get a result like this. What I'm showing you here, and I'm going to show you several of these, this is called a chromatogram. So the y-axis is called the total ion chromatogram or total ion current, and that's the response of an instrument called a gas chromatograph mass spectrometer, or GCMS. So this is the response of that instrument versus time. And the way the instrument works is that it'll take very complicated mixtures. You inject those onto a long, thin column, and those compounds will each adopt a velocity that's not exactly unique to them, but is very characteristic of that compound. So what happens is that things that adopt very fast velocity will come out quickly at relatively low retention times. Things that are very slow as they move through the column will come out very late at longer retention times. And you can see that each one of these spikes here represents a different chemical compound. So gasoline contains somewhere on the order of 300 different chemical compounds. So I've only identified in this figure 10 different compounds. Those are listed here on the left. But with chromatography and mass spectrometry, this enables you to really tease apart these mixtures and identify exactly what is present there. And chromatography like this is used not only in ignitable liquid analysis, but also in explosives analysis. So what is this problem then with the bugs? So I talked about Pseudomonas and that they're found in soil, and that the Pseudomonas can then actively start to metabolize or consume ignitable liquids. And the speed with which this happens is relatively rapid. So we're talking on the order of days that this will happen. And in the real world, it is not uncommon at all to collect fire evidence and then have it sit for a while. So it goes to the laboratory, it sits And during that time, if you have soil in your evidence or any kind of like degrading wood matter and that kind of thing, these bacteria will start to kick into gear and will start consuming the ignitable liquid. So if you don't do anything about it, if you let things go unchecked, then you can actually see, in some cases, total elimination of the ignitable liquid. So the evidence essentially has gone bad. It's gone to the point where there's nothing left and you can't identify it. And that would lead to a false negative. You'd analyze the evidence, you'd see nothing. If you didn't know that microbial action was going on, then you would say that there's no ignitable liquid present, but in fact there was. It just got consumed in the time it took from collection to actual analysis. So I can point this out to you. On the left-hand side are chromatograms of gasoline, just like the one that I showed you a couple slides ago. And this is what happens when gasoline evaporates. So this is normal during a fire. Fires, of course, are hot, and so therefore things that have low boiling points will evaporate more readily than things that have high boiling points. So if you look at these chromatograms, as you move from A, B, C to D, you can see that there's a shift in all the peaks. All the peaks seem to be shifting more and more to the right. And that basically means that all the boiling points are shifting. All the light or low boiling point compounds are being evaporated. The heavier ones are sticking around. And so you end up with a chromatogram still, but it's just been shifted. So this is important to understand this process, but it's not a deal breaker. You can still identify gasoline and a number of other liquids, even if they've been evaporated, sometimes even highly evaporated. On the right-hand side, however, is what microbes do. So the microbial action as you move from A, B, C to D, or I'm sorry, E, F, G to H, in that case, there's this whole cell loss. So you'll notice that by the time you get to the bottom chromatogram, which had been sitting for 22 days, which again is not far-fetched in terms of how long evidence sits around before it gets analyzed, you see very little of the original gasoline. So the microbes have done their damage. So the solution to this was preventing degradation, and we did that by using an antimicrobial agent. So the same thing that you would use to sterilize things in laboratories, or it's also used as, if you've ever seen, there's certain brands of plastic that are inherently antimicrobial. This molecule, called triclosan, is that same molecule that's getting incorporated into plastics. And for us, it was ideal. It was non-volatile, meaning it wouldn't interfere with all the fuel vapors, so it doesn't show up when you actually do the analysis, even if you put that on there. It's not going to corrode the can or somehow breach the container. Very potent. So if you look at sterile versus non-sterile, the amount of triclosan that was required in order to kill off all these bacteria in a live culture was relatively minimal, and it was long-lasting. So it lasted 60 days in our testing, and also relatively inexpensive. So the idea in terms of this application is that you would actually apply a solution of triclosan onto soil when you collect it. So you immediately put this chemical sterilizing agent on there that preserves the evidence. And so even 60 days later, you can go back and analyze it, and there's no interferences with the actual analysis. So this was an outcome that we devised from a National Institute of Justice grant. This got published, and we had a patent application that also resulted as an outcome of this particular project. So it was fun too, because this is bringing in one of our first partners, is that we had to do these tests on realistic samples. And so if you're testing fire debris, that means you need to burn something and then collect that material. So I just have a whole collage of pictures here when we went out with the Indianapolis Fire Department and we built Molotov cocktails. So you can see these wine bottles and beer bottles on the ground. A Molotov cocktail is just a breakable bottle filled with liquid, and then it's got a wick on top. So you can see these cloths sitting next to it. And then you start a fire by breaking the bottle with a wick. In this case, we put down bricks. and then the bottle would break, cause a large fire. And you can see that the soil here has been exposed. So we have soil that's been exposed. We then gather after the Molotov cocktail has burned its way out, gather that up and bring that in for testing. And we did a controlled study where we either preserved it or we didn't. And we saw a huge difference between preserved samples and those that were not preserved. If you're wondering what this picture is of the firefighter rolling around, you might see it by his ankle, but he actually caught on fire. He didn't know it at first until people started yelling to him that he was on fire. So he started to do the stop, drop, and roll. We put him out. He wasn't injured at all. The firefighters thought this was hilarious at the time. So we had them put on their full turnout gear and try to do this in as safe a way as possible. This is us students of various years and specialties gathering the soil. So all of this was gathered up, packaged into these paint cans that you can see here in the lower right and the upper right, and then transported to our laboratory. Okay, part 2, going to the dogs, meaning assessing explosive detecting canines. So the use of canines to find explosives has been a pretty well established practice for quite a long time. So this dates back to the 1970s and 80s, I believe. And you can see here on the picture on the left, this is a ATF canine team where you've got the handler who's presenting these gallon paint cans to the dog, which will then walk up, sniff into the open paint can, and then if there is explosive there, it alerts by sitting down. So here on the right, the crime lab or the crime laboratory will sit and wait and then get a reward. And the ATF system, they get food every time they do the alert. And other systems, they get a special tennis ball or toy, something that motivates them essentially. And so we've been looking at the use of dogs for detection of explosives for quite some time because it's something that I did prior to coming to IUPUI. I was with the ATF laboratory. And so one of my jobs there was certifying explosive detecting canines. I want to show you a canine in action. This is not an ATF dog. This is a dog from the UK Metropolitan Police. And what you're going to see, there's no sound, so it's just a video showing the dog being released and running down, say, 50 yards to the end of a range, and there's a series of posts numbered 1 through 6. And the dog has to find the post that has an explosive in it. In this case, the explosive is a pretty dangerous one. It's called triacetone triperoxide. It's a high explosive, but it's very sensitive to shock, heat, and friction. And so this was done off lead, meaning you don't lead the dog right up to something, you let the dog run, and then it'll do its sensing. So this gives you an example, though, of how quickly a dog can find something that's explosive. So you see that? It even does a quick double back because it's moving so fast. But the smell of explosives to a well-trained dog are really obvious. And they can be trained to be ridiculously sensitive, very selective. They can pick out the odor of an explosive even if there's a lot of other stuff going on. And as you can see here in this video clip, they can do it really quickly and without a human there to direct them. So they can be trained in a number of different ways. So this is showing you that again. 100 grams is about 2 cups of explosive, just to put that in perspective. So we're not talking about a ton of material. All right, so now here's some more chromatograms. This time we're looking at chromatograms from explosives. The top chromatogram is TNT, a very well-known explosive, trinitrotoluene. And the structure is shown right here. And this is a chromatogram of the headspace above TNT. So we're not actually analyzing the explosive, we're just analyzing the air that's collected above the explosive. And so in this case, you can see this huge peak here. This is for 2,4-dinitrotoluene. So this is not TNT. The TNT peak is this little teeny guy way over here. So the concentration of TNT in that space is actually relatively low. The concentration of DNT, which is an impurity in normal TNT manufacture, is very high because it's much, much more volatile. If you look at the bottom chromogram, this is a compound or a material called Nest, which is a non-explosive training aid. So all they do is they take silica, finely divided silica, and coat it with a layer of TNT. So the actual percentage by mass TNT is really low, about 8%. And so therefore this won't blow up. This is considered to be safe. But it shows you a very similar pattern. So here's the TNT, here's the DNT peak due to that. So because of that, and this is actually just echoing what I just said, because of that, people have had this thought that's been around a while, well, why not devise materials that either have explosives and won't blow up, so something that's diluted, or has no explosive at all and just has select chemical compounds on it that we know smell like explosives, so a facsimile of an explosive odor. Those are called pseudo explosives or pseudo scents. And they're commercially available. They've been marketed for use for all sorts of canine teams. But a lot of people have some issues there because there's pros and cons for using them. The pros are pretty straightforward, that you can have a simulant that shows you the odor but doesn't have anything in it. It's actually an explosive. So that means that they're safe. They are not hazardous unless you eat them. And there's really no special requirements for storage or shipping. The cons, though, is that it's typically not known what the chemical composition is. They don't tell you. They sell you this material as a proprietary material. And they haven't been exhaustively tested until we came in. So what happened with us is that we were asked by the Department of Defense to evaluate pseudo explosives and see to what extent they are effective. Can you use a pseudo explosive to train a dog and then have that dog find real explosives? Or if you have dogs that are trained on real explosives, can they find pseudo explosives? So the pseudo explosives are actually doing what they say they're doing by mimicking these odors. Then this should be true. This cross activity should happen. And we went to a fair amount of trouble and time to do this. We had to train up dogs from scratch. So we enlisted 24 different canine teams and then trained them in 3 groups. One group was trained on genuine explosives, one trained pseudo explosives from a certain brand, and then the third group was a different brand of pseudo explosives. So we had these 3 groups. It took a while to get them all trained up and accurately finding what they were trained to find. And then we did a series of tests where we had them find what they were trained to find. So the real explosive dogs would go along and try to find C4, composition C4, smokeless powder, or TNT, and they would do very well. So these things in bold show the overall accuracy with which the dogs were able to operate. But then when you gave them blind samples of pseudo explosives, for the most part, they ignored them. So the overall accuracy was really, really poor for many of these pseudo explosive compounds. If you take a look at some of these other columns here, you can see the same phenomena happened, where if you have a dog that's trained on a certain brand of pseudo explosives, the response rates tend to be very high. But they're very low when you actually find real explosives. So there's no correlation between training a dog on a pseudo explosive and it actually finding the real thing. So essentially it comes down to the canines will find what you train them to find. If you train them on pseudo explosives, then that's what they'll find. And but we don't care about pseudo explosives in the real world. We care about the actual dangerous explosives. And so this kind of blew a hole in the theory about using pseudoscents. Then last is talking about improvised explosive devices. In this case, I'm showing you a couple of pictures. One, this is an apparatus that we designed and together with the Indiana State Police Bomb Squad put together to actually gather residues of explosives. See these metal plates that are suspended along all the different axes. We would suspend a pipe bomb in the middle of this, detonate it, and then gather the residues that were present on what are called witness materials. So in a real bombing, witness materials can be cars, street signs, any kind of surface that survives the blast but is there to actually collect residue. And you can actually analyze that residue and determine what kind of explosive was there. We've also done several studies using pipe bombs and gathering the fragments that remain, because there's clues there as well. Not only is there residue on these materials, but the size and velocity of these fragments can vary significantly depending on what explosive is used and what type of container is used. So I've got a clip here. This is us out with the bomb squad doing pipe bomb explosions, but we used a high-speed video camera to record the explosion. So this is being recorded at 20,000 frames per second. So that's fast enough that you can actually catch the explosion happening in slow motion, ultra slow motion. And so what you're going to see here is the beginnings of a explosion, the full destruction of the device, and then we use computer software to track the fragments that resulted, so we can actually tell how fast the fragments were moving. When we had fragments whose mass was known, we were able to track the momentum and kinetic energy. So we're actually getting into the physics of IED explosions. And so let me just show you that. And here comes the tracks. So each of those colored tracks is a different piece that's leaving the scene of the explosion. We know the size scale in the video, and so we can actually back calculate velocity out of that. The other thing that's kind of interesting is that this line right here on the device is where the fuse was. And you can see that the explosion happens immediately around the fuse, which is kind of buried inside the powder inside the device. And so we could see differences in, for example, how plastic PVC devices and steel devices would fracture differently. And we were able to capture all that detail by using high-speed videography. We've done quantitative analysis of the residues. What you're looking at here is a heat map showing a deconstructed pipe bomb. Each of the end caps of the pipe is on the other end. This is the pipe body in the middle. And the shading is the concentration of nitroglycerin, which is one of the chemical residues of an explosive. And so we've even been able to do this where we can actually show or map out where the explosive residue is. And this has a direct impact on a forensic chemist's job, because when you're the forensic chemist, you don't witness the explosion, of course. All you get is the pieces that remain. And so this finding that all these end caps were significantly more loaded up with residue of nitroglycerin relative to the inside led us to make this recommendation that if you're looking for residue and you want to try to find the highest concentration and therefore be most able to detect that, you can look at the end caps. So the caps that make the ends collect that residue during the explosion. So some more pictures here. Upper left, we're looking at one of the pipe bodies actually being able to pierce through 3/4 inch plywood. So these explosions are tremendously violent. All of them were carried out at standoff distances to protect us and our equipment, and were done by the Indiana State Police Bomb Squad. Here in the middle is a picture of one of our collaborators gathering DNA. You can actually get DNA residue on a pipe from whoever built the pipe, and it survives. So not all the time, but it survives enough of the time that it's actually a viable technique to try to find a bomber by their DNA that they leave behind. We've got some shots of some dog testing that we've done with various agencies. Here's an example on the left of debris that you get from a pipe bomb explosion. So it can vary in size and shape depending on the construction and the explosive. Here's another view of that apparatus that we use to gather residue. So these are the witness plates that were affixed to that apparatus. I got a group picture of me and some of the students that were involved in some of these projects, as well as a large explosion here. Just for demonstration purposes, this is C4 and gasoline together, making a very large fireball. So we took part in a demonstration by the FBI that showed that. Okay, so to wrap up, measurement science or analytical chemistry definitely has a huge effect on forensic chemistry, because forensic chemists have to make a measurement in order to reach a conclusion, in order to either identify or compare physical evidence. And so for us, we have focused on preserving, characterizing, and explaining physical evidence, as well as other phenomena that are going on in either a fire or an explosion, and are relevant to those types of investigations. And it's definitely clear that none of our work would be possible without community partners. So we've worked with a number of different agencies, and I'll provide a list here next. And this is where the TRIP part of our work really comes into play, that we're looking at designing these new procedures and instruments to place them in the hands of forensic chemists and law enforcement, as well as public safety personnel, to directly affect their jobs, to make them more effective. And so along the way, there's been a number of different students that have been involved with this. So I've listed both undergraduates and graduate students that played a role either by doing their dissertation or thesis research in one of these areas. And our funding has largely come from either the Department of Justice or the Department of Defense, both of which have been very enthusiastic about some of the work that we've been able to do. And of course, we partner with the fire department, the State Police Bomb Squad. With the canine work, there's been many, many agencies that have taken part in those. I've just listed a few here. In order to get the data that we need to reach our conclusion, is really hinges upon these types of collaborations, which has been very rewarding. So that concludes what I wanted to say. Thanks very much. And I'd be happy to take any questions.
Thank you so much, Dr. Goodpaster. We'd like to invite you to unshare your screen so that we could see everybody, and encourage all of our guests to go ahead and show yourselves, turn on your video. And if you have a question, we'd invite you to raise your hand, unmute, and go ahead and ask the question. This is our chance to converse and to find out more about this work or the things that you want to know. So does anyone have a question they'd like to pose or a comment? Go ahead, Holly.
Thank you very much for your talk today, John. I really learned a lot. Microbial decomposition question really has less to do with explosives and the more to do with has the way that you have addressed microbial decomposition impacted other fields with similar challenges? So is it being applied, for example, with my work in cultural heritage and archaeological collections, we're dealing with similar issues. And I'm wondering if that has an application.
Okay, well, yeah, the direct application to fire debris has definitely happened. You mentioned explosives. Explosives can be degraded by bacteria as well. And so bacterial action on explosives will actually transform them from their native form into typically a more reduced form. So they'll take a nitro functional group and turn it into an amino functional group. So they basically will change the very nature of the explosive. With archaeological stuff, that's an interesting question, because maybe you should tell me more, but with that, the actual degradation of items is the key thing, as opposed to degradation of chemical compounds, correct?
Right, right.
Yeah, so there would be nothing keeping people from using this kind of approach for that. The problem, though, and I've worked some with the Indianapolis Museum of Art, with their preservation of art objects. I'm not sure how well it would go over to spray something with a chemical. You know,
Right. Right.
if that would be kind of verboten in terms of interfering too much with the object.
Right. Well, and you mentioned non-corrosive, but of course your level of preservation and the goal for antiquities would be different, right? So
Right.
we're trying to preserve in perpetuity.
Right.
And then I have a second question, if I may.
Sure.
And I can't help but, just be intrigued by this work with the crime lab. Love the play on words, it's so fun. But you said canines will find what they are trained to find. So again, forgive me for pushing this a little bit beyond the investigation of explosives, but I'm wondering about the use of cadaver dogs and whether their skills and training could be used to authenticate, for example, mummified remains. So
Okay.
again, I can't help but take everything you're sharing with us and sort of apply it to my world.
Mhm.
But we often get, for example, I'll give you a very good example. We often get bundles that are labeled infant mummy, for example.
Mhm.
Now, they may actually be looted mummies from tombs in South America, but they can also be faked very easily and sold for a lot of money. So this does intersect with the issue of law enforcement, but I'm wondering if dogs could be used, in that way to authenticate mummified remains.
Okay. Well, then I guess a question I'll need to know the answer to is, when they do this faking or forgery, are they using modern remains that are just masquerading as ancient?
Yeah. Well, and it could be as simple as, could cadaver dogs, crime labs, be used to detect what looks very much like a real mummy,
Mhm.
but there are no human remains inside. So can they go up?
Yeah.
So visually they've got the motifs right. Maybe they're even using, tea bags and coffee for staining to make things look very convincing.
Right.
But, if we don't have the ability to X-ray that particular piece, then are cadaver dogs able to walk up very quickly to a large group of items and pick out the ones that contain human remains?
Yeah. Well, I think my short answer is possibly yes, because cadaver dogs are trained to find recently deceased people.
Uh-huh.
And so there's a lot of work going on in terms of the chemistry of the odor of decay, human decay, and those odors are then used to train dogs. They've got the same issue with pseudo scents. They have their own version of a pseudo scent versus real tissue,
Right.
and training on the real thing. But a cadaver dog might be expected, if it's has no human remains in it, you would expect a negative result.
Right.
Right. And so that's indeed possible, I think. I've never seen it done. And cadaver dogs right now are search and rescue or recovery, kind of purposes. So, but it's an interesting idea.
Well, thank you again. It was a fascinating talk, and you've got
Thanks.
me thinking in all directions.
Well, thank you, Holly, for asking that question, because you are evidence of why we do this and the magic that happens when people share ideas and we think about them and translate them to other places. So yay, you get a gold star for the day. We have time for maybe one more comment question before we would begin to wrap up our time today in this conversation. Does anyone else have something they wanted to ask about or share a question or a comment?
Well, I see that there's a question in the chat about why specimens are stored in paint cans.
Yeah.
And so the reasoning is pretty straightforward. A paint can is strong, won't be easily crushed, airtight, and you can get them new and clean. And so they make a pretty ideal container for a lot of different types of evidence, including arson and explosives evidence.
So the couple of things that I took away from this that were just also very interesting to me was that you had made a comment that DNA survives on a pipe bomb, which was amazing to me that could happen. And that's a really important discovery, I think.
Yeah, that initial discovery was made by Michigan State University, my alma mater, actually. And since then, people have been able to reproduce those results. So for us, like between 10 and 20% of the time, we were able to recover DNA that gave us a full DNA profile, which is like a home run. If you get a full DNA profile, but then you develop a suspect, then that's fantastic. So, but it was only 10 to 20% of the time. DNA is a pretty rugged molecule, but again, we're talking about pretty violent conditions. But it's still, I would say, worth it because when you get that profile, it's tremendously powerful.
Yeah, that's amazing. And the other remarkable thing I wanted to just make sure everybody noticed was throughout your conversation, you really highlighted the connections with community partners, but also the involvement of students and how important that is. A lot of our work that happens here at IUPUI involves students from bachelor level all the way up through postgraduate degree.
Yep.
It's a great opportunity for our learners to have the chance to really get involved hands-on with this work and to see where that goes. Because they're with community partners, my goodness, the opportunities for what we do and finding those translations and connections is just amazing.
Oh, definitely.
So,
yeah, this will not be possible without students. That's for sure.
Right. Yeah. And it's a great opportunity. And it's just really nice evidence about the power of this place and what we do here. Dr. Bance, I noticed you unmuted. So were you going to say something?
I just want to thank John. It was a great presentation. You've done a lot of good work since you came. And as Steve just said, your involvement of students in it always sort of puts a smile on my face when I hear that you're going to talk about the work, both because somehow the image of an explosion was a pretty good one sometimes to an administrator, but not most of the time. But the other is Holly so clearly illustrated the ability to stimulate thinking across disciplines. And I especially like the question that the mummy raises because of what is the effect of the chemicals in mummification and how do the dogs apparently can be trained to sort those out, which is a huge advantage to learn.
Yeah.
And I thought the test you ran on comparing the Pseudo was a terrific one because somebody's created a business out of something without the data to show that it has the predictive validity and need in something as important as crime. So really terrific presentation. Thanks.
Thanks for hiring me.
Absolutely.
Well, thanks for all your work and for contributing here at IUPUI. And so what we want to do is close out this session and remind you that next month we'll be back again in September, and we've invited Sylvia Bagatti to come and talk about her work, community engaged work with the Latinx population. We have lots of other activities coming up. In October, we'll be doing our annual fall showcase, where you can learn more about translational work here at IUPUI on the 14th of October at 5 o'clock. And in that afternoon on the 14th of October, we'll also be introducing the Bance Community Fellow and the Bance Community Scholar Awards for this year, and having an opportunity to talk with some of our past awardees in a longer conversation to dive more deeply into their work. So there's so much going on. We hope that you'll take advantage of learning more about it. We're going to invite you now to go ahead and leave the Zoom if you want, so you can prepare for your 1 o'clock meeting. The rest of us are going to hang around here. If you wanted to say something to Dr. Goodpaster or you had a question, we'll be here for just a few more minutes as we wrap up. But we want to thank you for attending and for all that you do in partnership with IUPUI and the Center for Translating Research into Practice. Have a great day and a great weekend.